Hey guys, AP Chemistry Unit 7, we're in equilibrium. Let's go to the questions. So question number 1, here we have this formula. If you look at the coefficients 2, 1, 1, and 4, okay, that's going to be a big detail to this question. And you're also seeing the Kc, and I want you to notice something about the Kc. So if your K is greater than 1, remember, how do you get K? Well, let's take this step by step. K is equal to products over reactants, yeah? So if you have a K that is greater than 1, it means you have a lot of product, very little reactant, okay? If you have a K that is equal to 1, that means your products and your reactants are equal. And if you have a K that is less than 1, that means you have very little products, a whole lot of reactants, okay? And that's the scenario that we have right now. We have a K that is less than 1, so we have a whole lot of reactant, not a lot of product, okay? So let me kind of save this over here. And, okay, what we're going to do is, let's read the question first, okay? Let me get rid of this. All right, so you have a 0.1 mole sample of each of the 4 species in the reaction represented above is injected into a rigid, previously evacuated 1-liter container. Which of the following species will have the highest concentration when the system reaches equilibrium? Okay, now let's think through a lot of this, okay? All right, I'm going to say I have 0.1 here, I have 0.1 here, I have 0.1 here, and 0.1 here. Now, if this was the case, this has to get to equilibrium somehow. Now, let's draw what that graph would look like. And so I'm going to give you kind of a graph. Let's talk about it. We're going to have H2S coming down kind of hard. Okay, this is your H2S. And then you have your CH4, and it's not going to come down as hard. And the reason why is, if you're paying attention, the CH4 here has a 1 coefficient. This has a 2 coefficient. So that means those products will decrease, H2S will decrease faster than CH4 here. Now, in the same vein, you have something like CS2. And CS2 is going to come up by 1 mole, while H2 is coming up by 4 moles. Now, to be honest, I'm not necessarily putting these guys all in the right place. I need to let them end at equilibrium right here, dependent upon Kc, but I'm not doing that right now, okay? But don't worry about it, okay? Now, in a mole sample of each of the 4 species reaction represented above injected into the rigid previously evacuated container, which of the following species will have the highest concentration when the system reaches equilibrium? Look, this tells me this wants more reactant than product. Okay, it wants more reactant than product. If this thing wants more reactant than product, then these 2 guys will be higher than these 2 guys in the end. Right now, they're all equal. So it wants more reactant than product. And which reactant? Okay, so it's actually this graph. Let me change it a little bit. It's going to actually look something like this, right? It's going to ultimately, in the end, these. Ooh, and let me bring that down. Here's your. I knew I was going to do that. Damn it. Okay, but anyway, ultimately, in the end, these reactants are going to be higher than these products down here, okay? So how do we do that? That means if it's going to be between A and B. One of these are going to be higher because there's more reactant than product. Well, if that's the case, that means CH4 is going to be the highest of them all. The answer is B, because CH4 decreases less than H2S. Look, H2S decreases by a unit of 2, CH4 decreases only by a unit of 1. Okay, answer is B. All right, let's take a look at number 2. Now you have two NOs plus O2 yields two NO2s, and it gives you this really great piece of information right here that the delta H is negative. If delta H is negative, that means that this thing is what? It's exothermic, meaning heat is a product. And if you don't know what I'm doing right there, I'm drawing a little seesaw to demonstrate Le Chatelier's principle of equilibrium. All right, so what would let me kind of explain that through this question. Which of the following changes alone would cause a decrease in the K? Okay, first of all, the only thing that can change K is temperature. Okay, so it has to be between A and B. Now, who would decrease K? Again, K is products over reactants. Yeah? If K is products over reactants, and if we wanted K, like let's say we want K to go down, well, I would either have to lower the numerator, I would have to increase the denominator, one or the other. That would get me a lower K. So I either want products to go down or I want reactants to go up, okay? Well, remember, heat is a product here because this is exothermic. So if this is exothermic and heat is a product, okay, if I decrease the temperature, think about what this seesaw does, okay? We're on a seesaw, you got a bunch of kids called product on this side, okay? If I decrease the amount of that product or decrease the amount of the heat, the seesaw would get lighter on its right side, meaning it would have to create more product. Wait, I don't want to create more product. I want to decrease my product, okay? So the answer is B. I want to increase the temperature. Why would I increase the temperature? If I increase temperature and heat is a product, I shouldn't write that. I should write heat. And heat is a product. If I increase temperature and heat is a product, the right side gets heavier. So what does it do to reestablish equilibrium? It creates more reactant. It goes backwards. It's a backwards reaction. So that would lower, if I create more reactant, then I will have successfully lowered my K. Let's go to question number 3. Okay, BaO2 solid yields BaO solid plus O2. Okay, again, we're going to see this delta H, and this delta H tells us this is endothermic. If it is endothermic, let's go ahead and just add that here. This means heat is a reactant. Okay, it's on that side of equilibrium. Okay, a sealed rigid vessel contains BaO2 at equilibrium with BaO and O2 as represented by the equation above. Which of the following changes will increase the amount of BaO2 in the vessel? Okay, I want to increase the amount of BaO2. If I want to increase the amount of BaO2, that means I want this to happen in my Le Chatelier stress, okay? I want, because when this happens, when your left side is lighter, the reaction will move backwards to create more reactant, okay? All right, A, if I remove a small amount of O2. If I remove a small amount of O2, think of what it does to my equilibrium. If I move, those are kids on the right side of the seesaw. If I remove them, that right side will go up. That's wrong. I don't want that to happen. I will make the reaction go forward to get back to equilibrium because you want to be back at this. If I remove a small amount of BaO, the same thing is going to happen there. Okay, it's gonna remove kids on the right side of the seesaw, so they're gonna create more product, and again, that's not what I want. I want to create more BaO2. If I add HE gas to the vessel, I just want you to know this is a trick in almost all of the AP exams, like equilibrium questions. If you add an inert gas, it does not change equilibrium. It just doesn't do enough. But look at the last one. If I lower temperature, okay, heat is, again, a reactant here. It's on the left side. If I lower that temperature, I'm going to lessen the heat. The left side of my seesaw goes up. In other words, I'm going to have to create more reactant. And what is the reactant? It is the BaO2. The correct answer? D. All right. Question number 4. All right. This looks kind of familiar to many of you that have already done thermochem. It kind of looks like Hess's law. Let's make it make sense. All right, so I'm going to go, here's your solid S, 2 solid S's. Here are your O2, O2, that's 3 O2s. And here is your 2 SO3s, here's your 2 SO3s. And if you notice, what's going to happen? This 2 SO2 and this 2 SO2 are going to cancel out. Now you're adding these together, but unlike Hess's law, when you're dealing with K, you're going to multiply these two. You're going to multiply K1 and multiply K2 together when you add them. Okay, so let's do this. You're going to have 2 times 10 to the 105. You're going to multiply that by 7 times 10 to the 24th. And look, before you whip out your calculator, remember, this is a non-calculator portion of the test. So this is not, so let's just do this, okay? 2 times 7, okay, you can do 2 times 7, that's 14. 10 to the 105 times 10 to the 24, that's going to become 10 to the 129. Now, how did I do that? I added those exponents. You have to do 105 plus 24 to get 129. Now, look, obviously I have to move this decimal in, 1.4 times 10 to the 130. But even before you do that, just take a look at this number. 10 to the 129, the answer better be A, because look at all the other possible answers. It's not even close. And then for some of you who have teachers that emphasize significant figures, I mean, look at these significant figures here. 1, 1, 1, 1, 1. The significant figures are not going to come onto these kind of questions in the in the multiple choice because they are just not part of that, okay? Like, it's not what they're testing. They're trying to see if you know what happens here. So, again, when you see kind of like a Hess's law situation, but it's dealing with equilibrium, you multiply the two things. You don't add them, okay? All right, let's get to question number 5. All right, after the equilibrium above is established, some pure O2 is injected into the reaction vessel at a constant temperature. After equilibrium is reestablished, which of the following has a lower value compared to its value at the original equilibrium? So, all right, I kind of want to, I want to draw you this, okay? So what did we do? We had equilibrium, and then we injected some O2. So what the heck happened to the seesaw? The seesaw went like this because we added O2 at a constant temperature. After equilibrium is reestablished, how would equilibrium reestablish itself? It would create more reactant. It would go backwards to get back to equilibrium, okay? So which of the following has a lower value compared to its value at the original equilibrium? Well, if we went backwards, that means SO2 and O2 decreased while SO3 increased, right? So now you got to pick between SO2 and O2. Who decreased more? Well, come back to the original part of the question. The original part of the question said that O2 was injected. Well, okay, so O2 was injected, then it decreased. So overall, who's the only person, or who's the only substance here that only decreased? That would be SO2. The correct answer, the amount of SO2 has a lower value than it originally had. All right, question number 6. Okay, this one is a little annoying because of the math involved, but it's actually very doable. So don't think about it too much. Okay, You have your Kp, and if you guys remember what K is products over reactants, and so in this case you have K is equal to x squared times the well, actually this is Kp, so I should do it the right way. P x squared x2 times P y2 over P xy, and that is squared. Okay, that's how you do a K here. Now, products over reactants, make sure that this coefficient here becomes an exponent there. A certain gas, XY, decomposes as represented by the equation above. A sample of each of the three gases is put in a previously evacuated container. The initial partial pressure of the gases are shown in the table below. The temperature of the reaction mixture is held constant. In which direction will the reaction proceed? Okay, what direction is the reaction going to proceed? Okay, let's bring this down so we can kind of convert these things. And let's plug in the numbers. Okay, so you're going to have K is equal to, actually, you know what? Let me move things. Why don't you go over there? Ooh, see how I did that? That was cool. All right, so you're going to have, with your actual values, we're not going to be calculating K. We're actually calculating Q right now because we don't know if this is at equilibrium just yet. So let's plug in the numbers. You got 0.2 times 2, 0.0, yeah, over 0.01. I know people are going to be all like, why are you not using the correct amount of significant figures? Because it doesn't matter. Look at the answers on the answer choices. None of them have significant figures involved anyway. All right, so let's do these numbers. This number over here on the numerator is 0.4. This denominator is 0.0001. Okay, let me tell you how I think of this to be able to calculate this without a calculator. I think of this as 0.4 over 1 over 10,000. Right? So if this is 1 over 10,000, then what do? You multiply it. When you divide a fraction, you multiply by its reciprocal, right? So I end up having 0.4 times 10,000. 0.4 times 10,000 is 4,000. So my Q is equal to 4,000. Now, okay, my Q is equal to 4,000. My K is equal to 230. In other words, my Q, let me write this, my Q is a whole lot greater than my K. If my Q is a lot greater than my K, remember, this is products over reactants. How do I get my Q to lower? If your Q, you have products over reactants, if I want my Q to go lower, I either want my products to decrease or I want my reactants to increase. That'll make your number smaller because your denominator will get bigger. The correct answer, letter B. The reaction will form more reactant. Yeah, it's going to form more reactant because if it forms more reactant, you will lower your Q number to get to equal to K. Okay. Remember, all in equilibrium, everything's trying to get to K. All right, number 7. The reaction mixture represented above at equilibrium at 298 K and molar concentrations are that. Okay, so let's do this. So my K is equal to Z cubed over X squared times Y. I know I didn't write them in concentrations and brackets. It's okay. It's okay. Don't worry about it. It's not a beauty contest. Let me plug in numbers for these. I actually really like the numbers they give you here. So now we're supposed to calculate the value of equilibrium constants because these are actually numbers. But notice the significant figures are not a big deal, right? Like it's just not. And these numbers aren't crazy. Actually, I really like this number, right? Because I think of this 0.5, I think of that as 1/2, and 1/2 would cancel out with one of these 2's. I have 4 cubed, which is 64, divided by 2. What's 64 divided by 2? The correct answer, E. that's a more straightforward question. I mean, honestly, I hope the AP exam has a bunch of questions like that. I mean, those are the nice ones, right? All right, let's get to number 8. Or no, was that number 7? Yeah, number 7. Let's get to number 8. Okay, this one, I really like this question because of the math involved. Okay, watch. You're going to set your K again. For the system representative above, O2 and O3 are initially 0.15 moles and 2.5 moles, molarity, respectively. Which of the following best predicts what occurs at the system approaches equilibrium? Okay, so I'm going to write my K, or actually shoot. I keep saying K, I should say Q. I'm going to do my Q here. My Q is equal to O3 squared over O2 cubed. Let's put in the correct numbers. My O3 was 2.5 squared over 0.15 cubed. This is my Q. Now, okay, this is a really annoying math problem because, okay, let's say you don't know the square of 25 times 25, which is 625, but this is 6.25, okay? Then you have to find out the cube of 0.15. Now, I don't know what that number is. I mean, it's gonna be 0.15 times, what is it, 0.0225 or whatever. And look, a lot of you students are going to take a lot of time trying to figure out what that number is. You're going to be like, you're going to actually, write this 0.15 and you're actually going to multiply it out. But I don't know what that is, but okay, you know what? Let's make it, what if it was 0.1? It would just move this decimal one more over, yeah? So, okay, just humor me and let's not actually do the math. I'm going to write this. It's 0.00 like 2, right? Instead of 0.02. I'm just going to move the decimal over 1 because it doesn't matter. Look, the numerator is 6.25 times 10 to the 0, right? The denominator is like 2 times 10 to the negative 123, okay? All I know is that when I calculate my Q, pay attention here. See that O and that negative 3? That's going to become 10 to the 0 minus 3. Minus negative 3. In other words, it's going to become 10 to the 3. That's what my Q is. My Q is some number, right? Some number times 10 to the negative 3. What's the point? Look at the number they gave you here. 10 to the negative 56. That's astronomically small. I don't know what my Q is exactly, but I know my Q is some number times 10 to the 3. 10 to the 3 is 1,000. KC is incredibly small. All you need to know is that Q is gigantic compared to K. So, look, I know some people are going to be hung up on this. How did you get that? I didn't. I didn't actually multiply point. I didn't do this cubed. All I realized that it's only going to move my decimal so much. It's not going to move my and even if I was off, I wasn't this off. Like, look at how crazy those numbers are. Like, I could be off with the Q and it's actually 10, to the second power or 10 to the fourth power, but I'm not off by 56, right? Like, that's crazy. So the Q is gigantic compared to the K. If the Q is bigger than the K, that means I have way too much product and very tiny reactant. That means I need more reactant. That means the reaction will go reverse. All right. If the reaction is going to go reverse, I'm going to create more O2. So the amount of O3 will increase. The amount of O2 will increase, right? The amount of O3 will decrease. Oh, that's true. On letter B, the amount of O2 will decrease, but is Q less than KC? No, Q is greater than KC. The amount of O3 will increase, but Q is greater than KC? Nope, that's not true. The answer is D. The amount of O3 will decrease because it's going to go reverse because Q is greater than KC. Check mark. There you go. The answer here is D. All right, 4HCl plus O2 yields 2Cl2s plus 2H2Os. The equal number of moles in HClO2 in a closed system are allowed to reach equilibrium as represented by the equation above. Which of the following must be true at equilibrium? Okay, let's we did this a little bit earlier, but let's make like a graph of this. And okay, I'm going to say that HCl, okay, we'll do HCl, is going to go down pretty steeply. And O2 is going to go down not as much. Where am I getting this from? From the coefficients here, okay? The coefficients are telling me how much it's, like, there are going to be 4 HCl's used for every 1 O2 used. Now, Cl2 is going to increase, you know, by 2, but so will H2O. H2O is right there too, so this is both, they're going to increase at the same rate. Now, here's the thing. They didn't give me a K in this question, so, okay, let me shrink this down a little bit and copy it, because let me show you. If I don't know the K, I don't know whether this is more product or more reactant once it gets to equilibrium, right? Once it gets to equilibrium, is it like this? Or is it like this? Like, we don't know where this guy lies. He could lie below it. He could lie halfway through it. We don't know because it doesn't tell us, okay? So these are your two scenarios that you could have. You could have less products than reactants, or you could have less reactants than products. We don't know. So, okay, equal numbers of moles of HCl and O2 in a closed system are allowed to reach equilibrium as represented by the equation above. Which of the following must be true at equilibrium? HCl must be less than Cl2. Well, you don't know how to compare HCl and Cl2 because you don't know if it's this scenario or this scenario, okay? You don't know the K. O2 must be greater than HCl. Well, yeah, O2 must be greater than HCl because we started with equal number of moles. That's what that starts with. We started with equal number of moles, and O2 is only going to go down by 1. Right? O2 is only going to go down by 1 when HCl goes down by 4. So, yes, O2 must be greater than HCl. So, right now, I know the answer can't be A or C. All right. And I already know that it's not 1. So, okay, wait. It's not A, it's not C, and it's not E, right? So, now I guys got to figure out if number 3 is true, which is... it's all the work. But anyways, okay, the Cl2 must be equal to the H2O. That is true because they are the same mole-to-mole ratio. They're both going to go up at the same rate. So yes, the answers are 2 and 3. That means the correct answer, ting ting, is D. All right. Let's get to number 10. Okay. You have an equilibrium question here. Oh, let's start reading it here. Okay, PCl5 decomposes into PCl3 and Cl2 according to the equation above. A pure sample of PCl3 is placed in a rigid evacuated 1 liter container. The initial pressure of PCl5 is 1 atm and the temperature is held constant until the PCl5 reaches equilibrium with the decomposition products. The figure below shows the initial and equilibrium conditions of the system. Let's just write the K while we have time. The K is equal to P of PCl3 times the P of Cl2 over the P of Cl5. Let's make that 5 a little better. Okay, so here's our equilibrium. Okay, I'm going to bring that down with us because we're going to need it. And we're looking at this thing. Okay, here's when we had our initial. This looks like equilibrium. It looks like we're going to have to do an ice table. We're going to do that on question 11, though. Look at question 10. Additional Cl2 is injected into the system at equilibrium. Which of the following graphs best shows the rate of reverse reaction as a function of time? Okay, we injected Cl2. We injected some product in. So all of a sudden, you're going to have this spike, right? Like here and here. So it can't, now, because it's not going to, because you're going to inject it and then it's going to slowly decrease to get back to equilibrium. Like you're going to stress the system out, take it out of equilibrium, right? Like think of Le Chatelier's principle. You're at equilibrium, you're going to add a bunch of Cl2 on the product side. It's going to go like this. and then it's going to come back to equilibrium by producing more of the going reverse. So the Cl2 will initially increase and then it'll begin to decrease. So the answer has to be C or B. Now, I didn't really like the way this graph was drawn because initially, how much Cl2 did you have? Well, initially we had 0 Cl2. So it couldn't be C because if your initial amount over here was 0, right? If this is the initial amount 0, it can't go below 0, right? Like you can't have negative amount of Cl2. So this is wrong. The correct answer is B. But you guys get what I'm saying. Like this B, the initial amount was 0. Shouldn't that be down here? You know what I mean? Like I didn't like the way it was drawn, but the initial amount was 0. You spike up in Cl2, and as it decreases, oh, actually, I don't think that's what it's saying now that I think about it. But either way, the answer is B. All right. Number 11, using the same things. Which of the following statements about Kp of the equilibrium constant for the reaction is correct? Look at these. What is Kp? Is it greater than 1, less than 1, or is it equal to 1? All right, let's calculate it. I have these numbers here. Okay, and what we're going to do here, and let me kind of create some space. All right, what we're going to do here is we're going to set up an ice table. Okay, so all right, I have PCl5 yielding PCl3 and Cl2. My PCl5 is 1.0 initially. My Cl3 is 0. My Cl2 is 0. My changes, this is going to go down by X. This is going to go up by X. This is going to go up by X. And I get it. Right now, some of you guys, that are really used to, some level of ice tables, you're thinking, how are you going to do an ice table without a calculator? Isn't this going to get crazy? Nope, it doesn't. Relax. Okay, so this is going to become 1.0 minus X. This is going to be X, and this is going to be X. And you're thinking, do I need my n solve function on my calculator? No. Look, we know the total pressure of these three things at equilibrium was 1.4. So, in other words, 1.0 minus X plus X plus X is equal to 1.4. Notice what beautiful thing happens here with the math. Right here, this X and this X, you have only 1.x plus X is equal to 1.4. Therefore, X is equal to 0.4. All right. Substitute this 0.4. Ooh, what's going on? Substitute this 0.4 right here into here, here, and here, and ultimately substitute those values into there. You will get, ooh, I'm running out of space. Hold on. You'll get 0.4 squared over 0.6. This is 0.16 over 0.6, and I'm going to write it like that on purpose. Let me show you why. So now you have to find out, is your K greater than 1? Is your K equal to 1? Is your K less than 1? And I'm going to tell you, I made a mistake on this question when I was reviewing this right before I did this. I was like, oh, my numerator is greater than my denominator. Why did I say that? Because I'm an idiot. But the truth is, I saw 16 over 6. So I said my numerator is greater than my denominator, but this is really a 16 over 60, right? Like, I mean, it helps when you do stuff like that, just to visualize it so you can get through the question. Look, I'm gonna make little mistakes like that once in a while. You're gonna make mistakes like that once in a while, and it's just gonna be those things where you wish you had that question back because, I mean, why would we get something little like that wrong? Obviously the numerator is smaller than the denominator, so your K is less than 1 on this question. But if I make those kind of mistakes, I'm sure a lot of us make those kind of little dumb mistakes. The answer is B here. Okay, your K is less than 1. But just be careful is what I'm saying. Okay. All right. Then you have this really poorly. Sorry, this question is not even showing the reaction here. the only reaction that you need is reaction 1, and reaction 1 is on the other paper, so sorry about that. It printed out funny. But here, I'll rewrite that reaction 1. You have, we're on question 12 now, sorry. CaC2 plus 2H2O, and you have C2H2 and CaOH2. Okay, let me try to explain CaCOH2, calcium hydroxide. I always kind of like using the this analogy. All right, if I have, say, my wife. Okay, so my wife's a Disneyland fan. Say I'm the manufacturer for Disneyland, Mickey Mouse ears. If I have 100 Mickey Mouse ears, how many bands do I need to produce? Well, I need to produce 100 bands. And if I have 100 Mickey Mouse ears, how many ears do I have? I have 200. Okay, I double that, right? So that's the way I want you to think of it. If I have CaOH2, I have 100 Ca2 pluses, but I have 200 OH minuses. Okay, like try to keep that in focus. That's good. The amount of OH because of this coefficient right here will double. Okay, so that's the analogy for today. Now, CaOH precipitates when a 1 gram sample of is added to a 1 liter distilled is added to a 1 liter of distilled water at room temperature. If a 0.064 gram sample of calcium carbide, which has a molar mass, and by the way, the molar mass is given here, is used instead of all of it reacts, which of the following will occur and why? The value of KSP is equal to 8.0 times 10 to the negative 8. Okay, let me show you how I thought of this question. I said, you know what? This was glaring at me in the face. All right. They obviously want me to get this into the mole. 0.064 grams of calcium carbide divided by 64 grams per 1 mole. Notice how nice those numbers are. You get 0.001 moles of calcium carbide. Okay, now that's over 1 liter, so that's not just the moles, that's also the molarity, right? And then it says your KSP value of CaOH. Okay, so I'm thinking about this, and I said, which of the following will occur? And I was like thinking, oh, they gave me a KSP value. When you deal with a KSP value, you're dealing with. Let me just write this while we're here. You're dealing with the CaOH2 decomposing into Ca2 plus times concentration. Sorry, I'm writing this all wrong. Let me fix this. Okay. I'm talking about KSP, not the equation. Okay, so KSP is equal to the decomposition of the Ca2 plus and the OH minus, right? So there is no denominator because calcium hydroxide is a solid, right, before it's put in water, so there's no denominator. All right, but, okay, now let me put in the numbers. So this becomes X, and this becomes 2X. Remember the Mickey Mouse ears, right? But also because there is this 2 coefficient in front of this thing, this is squared. This is how the KSP looks for calcium hydroxide. That 2 in this this is not even the equation we're using. This has to change to, I should have just kept that up there, CaOH2 yielding Ca2 pluses and 2 OH minuses. So let me be clear. Not only does this 2OH double the amount of your OH, But it also, in addition to that, it also becomes this coefficient because when you do a K, you do products over reactants, and the coefficients become exponents. So it does double duty here. When you do enough KSP problems, this will become common. And you'll see that this right here is going to become 4x cubed. Okay, that's what your KSP is. And that might look new to you, but honestly, it's not going to be new to you very often. I mean, if you do enough KSP problems, you'll see the 4x cubed scenario very often. All right. Now I got to plug in some numbers for it. You know, calcium is a strong ion. It's going to, so if I have 0.001 moles of calcium carbide, guess what? I have 0.001 moles, or sorry, I should say molarity of calcium 2 plus as well, because it deconstructs. So in other words, that number is going to be placed in the X. So I have 4 times 0.001 cubed. I'll be honest, I wanted to look at this a little bit nicer, so I made this 4 times 10 to the negative 3 cubed, 10 to the negative 3. This became 4 times 10 to the negative 9 cubed. So look, 4 times 10 to the negative 9. I'm looking at that, and that's my KSP. Or that's my, I shouldn't say KSP, that's my QSP. All right, when I compare my KSP, 4 times 10 to the negative 9, 4 times 10 to the negative 9 to my KSP, I notice that my Q is less than my K, yes? All right, Q is less than my K, so Q is less than my K, Q is less than my K. All right. Now I got to ask myself, going back to this new formula that we created with the precipitation of CaOH, if my Q is less than my K, what does my thing want to do? If my Q is less than my K, it wants to go up. I want to create more product than reactant, right? If your Q is smaller than your K, you want more product to increase your number. You want more product. If you want more product, you want more of this, not more of this. You don't want more of the calcium hydroxide. You want more of this. If I want more of that, will CaOH precipitate or will it not precipitate? The answer is D. It will not precipitate because I don't want any more of the KOH. That was a really involved question with the KSP. There's a lot of things that you got to do, like to kind of learn KSP, but we'll go over that one as we go along. More KSP problems will show up. And I generally feel like KSP is one of the more difficult ones, but you will see like this 4x third is very common in KSP problems, so don't get too disheartened. Okay, now number 13. Okay, I was kind of weirded out by this question because solids don't play in equilibrium, so I know what they were doing, but I don't know. I got to get answers myself on this. Okay. Endothermic, because delta H is positive. That means heat is a reactant. So in terms of Le Chatelier, it's on the left side. Okay, the reaction reaction system represented above is at equilibrium. Which of the following will decrease the amount of CaO in the system? Decrease the amount of CaO. If I want to decrease the amount of CaO, I got to do this so that it creates more reactants, right? So which will decrease my CaO in the system? All right, if I increase the volume, if you increase the volume, you go to the side with the more moles. Which side has more moles? The product side. If I lower the temperature, it's going to go like this. Ooh, because heat is a reactant, and it's going to go this way. The correct answer is B. But let's just check the other two for giggles. Removing some of the CO2, if I remove some of the CO2, the right side will get lighter. Removing some of the CaO3 at a constant temperature. Oh wait, this wasn't the problem. If I remove some of the CaO3, it'll go like this, right? So it'll want to go back. No, 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 no. That's a solid. Okay, so solids don't go back there. Okay. All right. Number 13. Number 14. Okay, equilibrium. All right, kind of like a Hess law situation again. You have CH4 here, CH4 here. You have some of your H2O here, some of your H2O here. All right. And then you have your H2 here and you have H2 here. Oh, yeah, you have H2 here and you have H2. Now you got your 4 H2s, yeah? And then you have your CO2 here and your CO2 here. In other words, do you notice that you have to flip both of these? Now, here's the thing. In Hess's law, when you flip them, they become negative, right? It would become negative K1 and negative K2. But this is not Hess's law. This is equilibrium. When you flip an equilibrium, instead of products over reactants, it becomes reactants over products. These flip. Okay? So it doesn't just become negative. It becomes its inverse. So how do you calculate 3? Okay? Again, when you do kind of like a Hess law situation with equilibrium, you instead of adding them, you multiply them. So you have to multiply 1 over K1 times 1 over K2. The answer is D. That's tricky because, remember, in Hess's law, when you're dealing with enthalpy, a positive sign will become negative. Here, it doesn't become negative, it becomes the inverse. Reactants over products, not products over reactants. All right, number 15. All right, look at this one. It's all x's and y's. Now you have a couple xy's showing up. Now you have 3 xy's showing up, still 3 xy's showing up, still 3 xy's showing up. So right about here, that's where we hit equilibrium. X plus y yields xy. The particle diagram above illustrates the change that take place when x and y are placed inside the rigid container at constant temperature. Which of the following is a characteristic of a system at equilibrium that is best represented by the particle diagram? Okay, so what happens? The particle diagram shows that initially the reaction proceeds to the right to form products, which is a characteristic of a system at equilibrium. Okay, that's not true because initially, yes, this is true, that it initially proceeded to the right to form products, but that was because we only had the reactants in the first place. Initially, we don't have to have just reactants. We could have reactants and products, and it can work to form more reactants, or it can work to form more products. This part of the section is not true. The particle diagram shows that after 200 seconds, the rate of the reverse reaction is slower than the rate. No. Rate of the reverse reaction and the rate of the forward reaction at equilibrium are equal. So no, it's not slower. The particle diagram shows that after 200 seconds, there are no observable changes in the amounts of reactants and product, which is a character. This is true. Ding, ding, ding. The answer is C. Let's take a look at what D says, though. The particle diagram shows that between 0 seconds and 200, the rates of the forward reacts are the same, which is a characteristic. No. The rates of the forward reaction were faster, and the rates of reverse reaction were slower until it got to equilibrium. Okay? All right. We're going to take a break there. See you next video.